Alright guys, well I guess we can start. Today will be sort of in fact it will fit together with Monday's lecture better than I think sometimes these things dovetail. So today we'll be talking about isometry invariance and spectral techniques and lots of methods that are very, very close to my heart. In fact, some papers with my own name on them and a ton of papers that come out of Stanford. This is a topic that is very well liked and very familiar within our research group, as well as many others. By the way, before we start, a couple things. I posted homework 4 yesterday, so get started on that soon. It's one of these ones where the problems themselves are not that tricky, but the notation is like horrendous if you're not used to this sort of stuff. Right? You remember that the last 2 weeks we've spent tons of time going over like this whole new algebra, right, with D's and stars and charts and flats and, I don't know, pluses and minuses and other exciting things. And getting used to manipulating all these operators and having some intuition for what the D's and stars and charts and flats are doing, it takes a little bit of thinking the first time. By the way, something that helps me the first time that I did this kind of stuff, especially the discrete differential geometry thing is here, a little mini hint for the day. For example, let's say that I want to do like d delta alpha equals d beta, right? Like solve one of these problems that you see when you're computing the Helmholtz, the Hodge decomposition. One thing that I ended up doing, which helped a lot, is remember these things are all just matrices, and it's useful to remember what object you have at all times. So for instance, for that, maybe you expand this a little bit to d, and then delta is 1 star, d star alpha equals d beta. And what do you know here? Well, maybe you know that this thing is a 1 form, right? And that means that d of beta is going to be a what? Adrian knows the answer, but that's not fair. So d ups the number next to the form. So a d is a 2 form. Good, so this is a useful hint. And similarly, what do you know? Well, this is an equal sign, which means that there has to be a 2 form here. And we know that d ups the thing, so this is a 1 form. And then this thing is also a 1 form, and so on, right? So actually going through and making sure you know what the input and output is to each operator that you're going to be chaining together, which will actually be a considerable number, is an exercise that is worth doing because you'll actually get what's going on. In fact, my Helmholtz Hodge decomposition code was buggy for a long time because remember that we have this additional issue, which is that your D's and your stars in discrete exterior calculus aren't just about K-forms, but they're also primal and dual K-forms. Yeah? And keeping track of like when something is a primal 1 form and a dual 2 form and a primal 2 form, right? They're like 6 different possibilities here, and each time you stick one of these operators here, they do something different. For instance, right, so I'm doing this, I guess, in theory, so this is still a 1 form. Remember that star switching from primal to dual? But then next to this d, right, since d's add a number to your form, it's a 0 form, yeah? What does that mean? That means that this d and this d, even though you use the same letter, are actually 2 different matrices. Right? So kind of cutting through the notation and figuring out what you're going to actually have to implement in the end on this homework assignment takes a little bit of thinking. And Adrian's theory problem also helps with this, right? It relates it back to Dave and Carl and some of these things you know. So hopefully, I know this one's tricky and will be a little bit of a struggle, but I promise if you can get your way to the end of it, you'll be a much better Riemannian geometer for it. Anyway, so that's your note about homework 4. Since you're responsible for instructor took a little bit extra time to make sure the assignment wasn't going to explode on you, I gave you an extra day for your assignment. We should talk to the CA, Diana, to make sure that she gets your assignment. If you take all your late days, that she still gets it before grades are due. But I think that should be okay. You don't want to take all your late days anyway because you got a project due. Speaking of which, your project. You have one. I checked the spreadsheet with, oh yes? late days on the final assignment? I'm sorry? No, you don't, but you lose credit. And what I don't want is for your credit to go to 0 because it's worth it. So I will get back to you guys on that. Some reminders about your project. Remember that the project has that spreadsheet. You're supposed to put your topic on the spreadsheet to make sure nobody else takes the topic. I checked it the other day, and there were about 5 or 6 things, and there are more than that number of people in this class. So just beware, proceed at your own risk, but if you don't spend the 18 seconds to put your topic in the spreadsheet, somebody else might take it. And don't delete somebody else's project, because that's not cool. Finally, we're coming up on the end of CS 468. You can all breathe easy in a few weeks. I know that we have a number of grad students and people in this class that have taken it with a particular application or topic in mind. This is sort of your last, say, if there's some topic in differential geometry that you've just always wanted to know about, then feel free to email us and we'll try to incorporate that into some of the lectures toward the end. Especially if your topic happens to intersect with the topics that we've sort of outlined for the rest of the course. So anyway, that's our procedural stuff for the day. Any questions before we go dive into all this stuff? No? Cool. All right. And as usual, if you have questions, the piazza and all that stuff is there for you. Okay. So on Monday, as usual, we defined all kinds of different notation and terms and so on. In this case, involving the intrinsic geometry and isometry invariance and so on the surface. So I think we'll spend a few minutes sort of motivating from a discrete perspective why these notions are very important, and then go over some techniques that make use of isometry invariance to solve problems that we care about. So to me, the motivation for a lot of these types of algorithms is that when we talk about shapes being the same, we don't necessarily just mean that literally you take the same object and you just replicate it, right? For instance, in this set of teddy bears here, you can see that we have a sort of a class of teddy bears, yeah? But really within this class, obviously his arms are in very different positions, his legs are moving up and down. In fact, there are 2 types of teddy bears here, right? And somehow we want to build into a lot of algorithms that we come up with in geometry processing some amount of invariance to these sorts of changes in structure. Now, why do I say some amount? Well, at some point you do want these shapes to look different, or else we haven't done anything interesting. Yeah, so there's an interesting trade-off here as to what you want to look the same and what you don't want to look the same. And that's going to be the theme today. So what are some applications that we might have in mind that we want to be deformation invariant? Well, off the top of my head, as a person that does lots of research in deformation invariant type algorithms, I can think of a bunch. But there's some use cases for these sorts of algorithms include things like segmentation. So let's say I give you a mesh of a human, and I want to divide that human into meaningful pieces like arms and legs and torso and head. Then to some extent, we don't want to take our human mesh and deform them a little bit and get a completely different segmentation we had before. Similarly, for symmetry detection, something that we'll come back to later in today's lecture if we have time, is the idea of an intrinsic symmetry. Now, humans can be extrinsically symmetric. Yeah? If I stand like this and I put my arms out on the side and I measure the angle of my pits very carefully, then I can probably achieve some approximation of extrinsic symmetry. Namely, if you took something and just cut me in half, which you might want to do after homework 4, then you could take one half, flip it over a mirror, attach to the other, and you'll have me back again. Very uncomfortable. However, if I then bend one of my arms and leave the other one straight, I no longer can apply my favorite techniques from middle school geometry class to understanding what kind of a symmetry that is, right? Somehow my body still has some left-right symmetry, right? My brain hasn't all of a sudden decided that my left and right-hand sides are totally different things. But being able to express that is an intrinsic way to understand symmetry. Something else I might want to do is be able to globally describe a shape. So for instance, actually, I guess the 2 things right underneath it are instances of this task here. Right? So maybe I have a whole database of teddy bears, and I want to be able to find the teddy bear in a particular pose. Or maybe I want to find the teddy bear in a database of teddy bears and cars. Right? There are lots of different tasks here that you want some amount of deformation invariance that are quite useful. And finally, things like feature extraction, alignment. Alignment is a very important one in computer graphics, right? If I have Brad Pitt acting in front of one of my 3D scanners and he's deforming himself and moving his arms up and down and so on, and what I want to do is take his motions and project them onto happy feet, which would be a very expensive production of happy feet, then I need some amount of invariance to understanding that this is a guy with articulated arms and legs in front of my camera, right? And being able to separate who that guy is from how he is deforming, right? So basically what I'm trying to communicate here is that having some basic models of how objects deform, how they vary from one another, and so on is a very important task in differential geometry, and one that we think about both in theory and in practice. So today we're going to focus in on, in some ways, the most simple, and in other ways the most complicated model of deformation, and that's isometry. Isometry simply means that you bend without stretching. Right? Now, what is an example of something that actually admits isometry? Well, gosh, there's only one person in this room that takes notes on paper anymore. It's interesting. Lots of laptops. Cool. Anyway, if you had paper in front of you, what you would notice is that paper doesn't stretch, it tears, right? So I try to take a piece of paper and I deform it, right? Particularly if I take that piece of paper and I just draw a curve along that piece of paper, and then I bend it any which way, the length of that curve doesn't change, right? And that's because the sheet of paper deforms isometrically. This would be different from drawing a curve on a piece of elastic, right? Because a piece of elastic, I take the two sides, grab them, and yank them out like that, right? And then my curve just got longer. That's not an isometric deformation, and we'll return to that, I think, either next week or the week after, when we talk about as rigid as possible in some of these other techniques. So, of course, mathematically, how do we define isometry? There's sort of a local definition and a global definition, and in differential geometry, there's a very deep connection between these two things, and one that I don't think we'll get anywhere close to proving. But anyway, you can think of an isometry as a function between two objects. I should have drawn a picture of this. So let's say that I have, unfortunately the instructor is a terrible artist. So here's one guy, and here's another guy whose arms are kind of up. His head also shrunk a little bit in the meantime. But anyway, if I have a function that takes points on this guy to the corresponding points on this guy, and I say that that function is isometry, what does that mean? Well, it can mean a couple different things, depending on whether you're a differential guy or a topologist, I guess. But one way that you can define this is a global isometry, which means that pairwise distances are preserved. Right? Namely, if I take a point x, we'll call this one x, and another point y, right? And I take now the corresponding f of x and f of y, right? Then I can either measure distances along this surface, right? We've already talked about distance measurement, right, using these geodesics. Or I can measure distances on this guy. And if my map's an isometry, then this process is guaranteed to give you the same number. Yeah? Alternatively, right, on the last couple of weeks, we talked a lot about the metric of a surface, right? The idea of how you take inner products and locally measure angles and lengths and so on, right? And locally, what happens in isometry is that your metric, right, this little inner product object, is preserved from one surface to the other. Okay? Did I get this backward?
No, it's fine.
Okay.
F lower star is df, the differential.
Oh yes, I'm sorry. I switched textbooks on you guys. Yeah, this thing is df. I don't think we've seen pullbacks either, actually.
No.
You can ignore the first one, and the second one, if you think of f lower star as df. These are our equivalent definitions.
You draw a picture of, I'm going to do it, but draw a picture of the lower one.
Yeah, so the lower one, this localized version of isometry, right? Remember that df, if f is a function between surfaces, then df is a way to take tangent spaces to other tangent spaces. So in particular, what this bottom statement is saying, yeah, is that if I take two vectors over here, centered at x, say, and now I map them forward under df, right? So that's going to be two vectors on his tangent plane at the corresponding point. right? Then I can take inner products on either side and I'll get the same number. Right? And there's a very deep sort of connection between these two definitions of isometry that make them equivalent under some additional conditions in your math. Cool. So what do we kind of expect for isometry invariant techniques? Well, we sort of expect them to be the types of algorithms that we can measure as an ant walking along a surface, right? Namely, if you look at your feet and you measure distances and angles and so on, right? Then all the measurements you make, sort of just by your perspective as this ant, are completely intrinsic, right? And the types of algorithms that we'll talk about have a sort of similar viewpoint in life. Now, our hope for isometry invariance is that, to some degree, an isometry invariant algorithm is one that's invariant to certain types of deformation. Right? So maybe, and sort of the way that many of these papers motivate the methods that they use is they say, well, look, maybe I have a given model in a bunch of different poses, and really I'd like my algorithm to behave the same on all of these different guys. And making my algorithm somehow isometry invariant guarantees that. Now, how many people agree with this? How many people would raise their hand if I asked a different question? That's what I thought. You all happen to be right, although I'm not sure that you were right intentionally. What was that? Yes, you were 100% right, and I'm excited to see that you are all following lecture. And the reason for that is that isometry invariance is a very, very, very strong condition. In fact, there are very few surfaces on the face of the Earth that can deform isometrically at all, right? And those surfaces tend to look like this, right? And namely, sheets of paper. In fact, we can formalize this, and we won't in this class, to literally prove that any other surface likely will not have this behavior. Yeah? So when we talk about isometry invariance for algorithms, something that we have to keep in the back of our head is that it's not enough for our algorithm to only work when your surfaces are 100% isometric. Right? What really matters is that your surfaces are approximately isometric. And what is our intuition for that? Well, let's say that we have human models, right? For the most part, when I'm walking around this classroom, I do deform isometrically. Namely, I have bones sitting underneath my arms that are just these rigid objects that hopefully I can't really bend all that much. Right? So what's going on when I deform and I bend my arms is very localized stretching, right, followed by these big rigid pieces. And our intuition is that a lot of times this type of structure, right, whether it be articulated or not, appears in the type of geometry that we know and love. Is that always true, right? If I want to write algorithms for processing brain scans, is an interesting question that came up in our group, right? Can we assume that brains are approximately isometric to one another? Probably not, right? And so you need a different class of algorithms for dealing with that type of data. As I mentioned before, by the way, there's a completely separate thread in discrete differential geometry on exact isometric deformation. In fact, if you're interested in this sort of thing, this happens to be a field I know well. This is an image from one of my papers, and where this comes up a lot is in cloth simulation, right, where pieces of cloth deform approximately isometrically with some localized stretching. And being able to deal with that in a smart differential geometry kind of way is very important. Surfaces that deform isometrically in an interesting way have sort of two names. The smooth version is a developable surface, and the creased and flat version is origami, and these are very intricately linked areas of mathematics that we will get nowhere near touching today. So anyway, the main sort of vocabulary word that you might want to know is rigidity for now. Namely, that most surfaces that you encounter in the wild are rigid. In fact, generically, all surfaces are rigid, I think. But the big idea is that if you just randomly generate some blob in space, chances are it's going to be a rigid blob, even if I make it out of paper. But it might be the case that approximately this thing can still deform in some nearly isometric way. So anyway, hopefully now we have sort of our happy and our sad sides of the story, but let's dive into some concrete aspects of particular problems that we might want to solve in an isometry invariant way. Right? So one of the most simple tasks that shows up every which way, those of you that have taken a computer vision class have seen this pretty much exhausted to death, is the idea of coming up with a descriptor. right? In computer vision, we talk about SIFT and SURF and so on, right? The idea is that these are somehow some characterization of the local behavior in the computer vision case of an image near a particular pixel, right? In our case, what do we want to do? Well, we want to take a function from each point in our surface into Rn, which is basically going to just give us n numbers that describe the geometry of our surface near that point. Right? We can think about all kinds of applications, including some of the ones I've already mentioned, that might make use of these sorts of descriptors, right? Once I can write down interesting information about geometry, I can try to match these points together, align them, and so on. Right? This is oftentimes the input to a larger pipeline. So as I already mentioned, I guess, some tasks you might want to do with the descriptor include understanding the local shape near a point. Right? This is different from coming up with a descriptor for the entire shape. Right? What I'm saying is this is a descriptor for each point separately on a shape. Yeah? These are two separate tasks, both very important. And maybe one way to think about that is one to describe a particular point or vertex, his role on a surface within the larger piece of geometry. Notice these tasks are slightly different, right? Maybe characterizing local geometry only depends on some neighborhood around your feet, whereas defining your role makes you look at the entire surface and then gathering data back to the point. But both of these are legitimate approaches to coming up with descriptors that we might want to explore. And this is not a new task for us in CS 468. Now, in particular, we already have defined these two things called Gaussian and mean curvature. Hopefully, we haven't forgotten those from a couple weeks ago. And these are just point-wise descriptors of a shape, right? They're very, very, very localized ideas of how a surface bends, right? And in fact, we'll come back to one of these. You probably guess which one as a particularly important descriptor, as a sort of initial example. So what are desirable properties? Well, maybe they distinguish different points on the surface. Yeah, if you just give a constant function, it's not a very interesting descriptor. You want them to be somehow stable, and this is a word that we'll come back to, right? There's two types of stable. Maybe I have a noisy scan of a surface, and I don't want my descriptor to change all that much. Or maybe my surface deforms under isometry, and I don't want my descriptor to change very much. Two very different types. And finally, I might want my descriptor to be intrinsic, which we've now motivated to death, but basically is some amount of invariance to a particular type of deformation. In particular, again, the descriptor would be variant under rigid motion, embedding without stretching. So, thankfully, we proved on Monday that we already have an intrinsic descriptor for our surface. Anybody remember what it is? Gaussian curvature. Thanks, Trent. Right? In particular, Adrian at least motivated this theorem, right? Which approximately translates to Gauss's totally awesome theorem. And what does it say? Well, one statement of this theorem, which is the theorem egregium, I still can't say it right, is that Gaussian curvature is intrinsic. If I take a surface and I have an isometric map from that surface to another one, the Gaussian curvature will be preserved. Anyway, that's one way to state this theorem. So of course, the question you should ask is, well, is that the end of our story? Well, not quite. So for one thing, as you might have seen on, I think, homework 3, lots of these measures for Gaussian curvature have really pretty theory behind them, but in practice, they're quite noisy. Right? So I implemented one, and I think this is actually after a little bit of smoothing. You can see that, yeah, it's kind of intelligent about hyperbolic and parabolic is the surface and so on. But locally, there's a ton of noise, right? There's a second derivative object on this very, very coarse approximation of the surface. Yeah? But more importantly, from a theoretical standpoint, Gaussian curvature doesn't characterize a point on a surface. Right? So for example, on this car model, the entire hood of the car here is the same number. Right? So if I'm trying to come up with a descriptor that helps me distinguish all these points from one another, well, I haven't done it yet. We do a little bit more work. Now, in fact, remember that in week, 3 or 4, we mentioned that if you have Gaussian and mean curvature, then you can, to some extent, reconstruct a 3D surface. So a question that I should ask at this point is, okay, so why not throw mean curvature into the pot and then end our story? It's not intrinsic. Mean curvature is the opposite of intrinsic. It is like the non-intrinsic piece of a piece of geometry. In fact, if you write a piece of code for simulating cloth, right? Remember that cloth sort of is a developable surface, right? So what is the energy term that wants the cloth to not just crumple up into a ball, but rather, kind of spread out and not bend as much? Well, bending energies, all you do is you take the mean curvature of your surface, you square it, and you integrate it along the surface. That's the bending energy of your surface. Very extrinsic quantity. So anyway, a more desirable descriptor might incorporate some neighborhood information in an intrinsic way, and is stable under some small deformations. I guess these slides repeat themselves a little bit, but that's okay. Well, what other intrinsic objects have we discussed so far in CS468? Well, thankfully I haven't exhausted our entire library yet. In particular, last week we talked about this either discrete or continuous, doesn't really matter yet, de Rham complex of all of these different differential forms, right? We had 0 forms, 1 forms, 2 forms, dual 0 forms, dual 1 forms, and dual 2 forms, and you'll have the pleasure of manipulating all of these on your homework. It's going to be so much fun, right? And then what did we do? Well, on top of all these different objects, we generated a bunch of different operators that can take me from one to the next, right? D's take me from K forms to K plus 1 forms, right? Stars take me from K forms to dual K forms and back, and so on. And we can chain them together to make all kinds of interesting PDEs and differential looking objects on the surface, right? Well, it turns out that if you look back at how if you look back at the theory lectures, then the derivation of all these objects is completely intrinsic, which means that anything that comes from this complex is fair game when it comes to coming up with isometry invariant techniques. And what is one super, super important object that we proved comes from this complex? It involves cotangents, and we've seen it like 25 times now. They're all giggling, so I think you know what it is. The Laplacian, right? Remember, I mentioned to you guys that one way to write down a Laplacian operator, right, is to write d star plus star d star d. Right? In fact, one of these two terms vanishes if you do the Laplacian for functions of 0 forms. Right? We talked about all this. And when you take his eigenstuff, for example, what comes out are these nice vibration modes for your surface, right? Last time we had eigenhomers, this time we have eigendogs. And anything that we can compute just using Laplacian is an intrinsic quantity, because the Laplacian's intrinsic. Yeah? So why might this be useful? Well, for example, the Laplacian is enough to determine how things like heat flow happen on a surface. Right? So you see how I'm like slowly taking this itty bitty thing that I've defined, right, isometry, and just kind of slowly sticking more and more hammers into my toolbox, right? We can go from that to this complex of D's and stars, Laplacian, to now physics happens intrinsically, right? And so these are all things that we can think about, and isometry maybe is sort of a very deep notion in that sense. So what would be an intrinsic statement about heat flow would say that heat diffusion isn't affected if I bend a surface. Right? Namely, if I take an initial distribution of heat on a sheet of metal, and then I bend the metal without stretching it, right? And then I take these two, the first one and the second one, and I diffuse the heat at the same time, you'll see the same pattern on both surfaces. Intrinsically. Now, of course, if I crumple the piece of metal and heat can conduct from too far away points, then all hell breaks loose. But assuming that doesn't happen, we're good. And this is sort of an intrinsic physical effect, right? Same thing goes for waves. Well, this is enough to define one potential point descriptor that's a much stronger one than Gaussian curvature. And that's this thing that was introduced a few years ago called the global point signature, or conveniently, the GPS. Right? So here are our eigenhomers. And remember that each eigenhomer is nothing more than a function on the surface. Right? In fact, what we'll say is that each eigenfunction is phi 1, phi 2, phi 3, and so on. And then what's going to be the descriptor of a point P on Homer? All I'm going to do is take the value of each of my eigenfunctions Laplacian and just stick them together. How long is this vector? As long as you want it, right? The Laplacian has an infinite spectrum. Of course, as a matrix, it has a finite one, but if you go out to the size of your matrix in terms of how many eigenthings you compute, you'll be waiting for the rest of your life, and you'll get a lot of useless numbers. But that aside, at least if you take the first, say, 100, 200 values within this, you get a descriptor of a point. Right? For technical reasons, he scales them by the eigenvalue that comes out. That's not terribly important for our discussion right now. And why would the GPS be useful? Well, it has a lot of cool properties that are quite important. So one way to think about a descriptor is that it's an embedding of your surface. There's a little bit abstract. Maybe I should draw a picture. Right. So let's say that I compute the first like 100 GPS coordinates of each point on my surface, right? Then if I have my surface, right, our same doughy guy here, right? Then we can think of the GPS as a map from each point, P. This is just some function to some point in R, R100. You do 100 eigenvalues. Yeah. So this will be the GPS. Right? And each point on your surface is mapped to some other point in this space here. So in some sense, all that I've done is taken the geometry of my guy sitting in R3 and lifted him to some weird geometry sitting in R100, and we'd like to be able to understand the shape in this space. Does that make some sense? It's an abstract way to think about descriptors. If you don't like it, then you can kind of ignore it. But it turns out that this makes stating a couple of these theorems a little bit easier. So let's say that I have Homer, and Homer doesn't intersect himself, right? He doesn't stick his arm through his belly or anything too bizarre. Then it's quite easy to prove that if your surface doesn't self-intersect, then neither does your GPS embedding. It's a very slick way of saying something pretty simple, which is that if I take two different points on a surface, they'll have different coordinates in their GPS space. Why do I know that? Well, one way to think about eigenfunctional Laplacian, I guess we didn't really cover this in course UCA, is that they give you some notion of Fourier analysis on your surface. Right? These look like vibration modes. In fact, if you were to do the eigenfunctional Laplacian on just like an interval, you would get cosine and sine and all of our favorite things. Right? And what do we know is you can take any function and write it in terms of his Fourier coefficients, and I haven't really lost that much information. Right? So what would happen if 2 points on my surface had the same GPS coordinate? Well, in particular, what that would mean is that every single one of these eigenfunctions coincides at that point. Okay? They all have the same value. But why is that a bad thing? Well, what that means is if I take any function on Homer and I write him in his Fourier basis, that function's got to have the same value at P and Q, right? Because every single basis function has the same value at these 2 points. But it's pretty easy to construct functions that are different at just some pair of points on the surface. Yeah? So that's enough to prove that the GPS embedding for each point is unique. Yeah? Does that make some sense? Maybe, sort of, intuitively. Cool. What other properties does this have? Well, the GPS is isometry invariant. I think we studied that one to death, right? It comes out of Laplacian, so we're good. But the GPS also has a couple negative aspects. For one thing, many of the properties that are very important for the GPS, and a lot of the other descriptors we'll talk about today, assume that all of the eigenvalues that come out of your surface are unique. Right? So for example, what happens on a sphere? Or really any symmetric object, but a sphere is a good example. Right? Well, the sphere might have some eigenfunction, right, that has some peak in the middle of your surface. Right? But by symmetry, that means that there's another eigenfunction with the same eigenvalue that has a peak just rotated 90 degrees. I'm not drawing this very well, but hopefully you get the kind of idea. Right? Well, notice what was our definition of the GPS was that I took the first eigenfunction, the second, the third, and so on, and coupled them all together. What is the first eigenfunction of the sphere here? Well, we don't know, because there are two with the same eigenvalue. We can't separate these out. And so this isn't such a great method from that perspective. In addition, you might have eigenfunction switching. So maybe my surface deforms mostly isometrically, but not quite. And I have two vibration modes with very similar frequencies. It might be the case that when I stretch out some little itty-bitty piece of my surface, the two frequencies for the two modes swap. Right? Well, that was a continuous motion that just happened, a discrete thing happened in our GPS, namely the ordering of those two coordinates flipped. Right? So if I try to match those surfaces, this algorithm will fail. Plus, either a drawback or a positive aspect is this is a very non-local thing, right? Each coordinate function spans over the whole surface. But the GPS was sort of the earliest example, or one of the earliest examples of sort of a more generic technique, which is to understand behavior, Laplacian, and PDEs on a surface as a way to characterize points. But remember that it doesn't begin and end at vibration modes. There are lots of other equations we can solve. For instance, as I already mentioned, I guess, we can solve the heat equation on the surface. And notice that the heat equation only depends on the Laplacian structure. Right? I haven't incorporated the metric in any other way. All that Gij stuff is stuck in this triangle here. Yeah? Similarly, I can solve the wave equation, right? If I give you some, if I think of there being these little infinitesimal, bumps on the surface, and I give the bunny a little bit of a flick, I can trace how the wavefront moves around. It's just some other equation that I can write down that's just as easily solvable, only in terms of Laplacian. We have all these different model physical equations that we know that only involve that delta operator. This is great, right? Because they're all intrinsic. Hopefully we get the main takeaway from this today. So we'd like to use sort of how your bunny responds to heat and waves as a way to characterize its shape. Now, why does it make sense? Well, let's say that I'm diffusing heat on this whiteboard, I suppose. I put a little bit of heat here, and I diffuse over time. What's going to happen? Well, the heat's just going to spread out, and such is life, right? If I take a sphere, or my coffee cup here, and I put some heat on one point, what's going to happen is eventually you can have all kinds of interesting behavior, right? The heat can diffuse around the outside and then come back, right? Heat can't come back on this whiteboard, it just keeps going. And so somehow understanding these sorts of physical effects is one way to kind of get a toehold into understanding the shape and both locally and globally of your surface. Yeah? By the way, I don't think I'll bother spending time on this, but you can, if you write down the eigenbasis of the Laplacian, you can solve the heat equation directly in this basis. This is something you might have seen before, but not realized it in our analysis. Yeah. So what's one example of a descriptor that might use this sort of behavior? Well, a very popular one, at least as of a couple of years ago, is something called the heat kernel signature. Well, what does the heat kernel signature do? By the way, the expansion in the eigenfunction basis here is important for how you might actually compute these things. So this is something you should return to, but I think we'll omit for now. But the heat kernel signature, physically, is a very simple thing. The heat kernel signature, now remember that our GPS was already this infinite set of coordinates, but it was at least a discretely infinite set of things. Now we're going to say that we'll associate with each point on our surface a function of time. What is that function going to be? Well, let's say that I'm at a point P, I'm going to put a little delta of heat at point P, right? And then I'm going to watch over time what happens to this little bit of heat as it spreads out of the surface, right? It'll get wider and wider and wider and diffuse to different places. And so this is a function of time, but it's a function of two things, right? A function of your starting point, P, and the amount of time you've diffused, yeah? So what am I going to do? I'm going to slice that function through P again. That is, I'm going to say that the heat kernel signature of P is the amount of heat left at point P only at time T. That makes sense? So I put this little itty-bitty amount of heat right in my toes, and then I let it diffuse, but the only thing I can do is look back at my toes and feel how warm my feet are, right? And I'll just measure that function as a function of time. And it turns out that the heat kernel, so here's what the heat kernel signature looks like. So you'll notice that at very small times, these things look quite similar when you have similar points. In fact, as you go, as time goes to 0, you can show that the heat kernel signature looks a little bit like Gaussian curvature. It's funny how these things are all connected to one another. But then as time goes out, so this is the heat kernel signature as a function of time here for 44 points. 1, 2, 3, 4, which there are on his 4 toes. What happens? Well, so 1 and 2 have different behavior for 3 and 4, and we look back at our surface, and we realize that these are the front 2 toes, and these are the back 2 toes. Why is that? Well, at small time scales, the heat repeated 4 times. But then as you let heat diffuse out to a longer time scale, where it's starting to reach things like his head and his midsection here, right? Now, heat that started out in the stove can maybe diffuse up this way a lot faster than heat can over here, right? And now these points start to distinguish themselves. Right, so the heat kernel signature has this nice sort of multiscale property, right? At very small scales, it just measures the curvature of the surface. At very large scales, it measures kind of global interactions between points and so on. And in fact, many of the things that we already showed for the GPS are also true for the HKS. It's isometry invariant, now it's multiscale, right? This diffusion time has to do with sort of what neighborhood you're interested in. It's not subject to this switching anymore, because we haven't used the eigenfunctions directly. It's very easy to compute. And it's related to curvature. Life is good. But there is still, oh, sorry.
On the plot from the previous one, so this is, at the end, they would come back together, right? I mean, to infinity? Shouldn't they?
Yes.
Because at some point,
at some point, yeah. So if you take, actually that's 100% right. The infinite amount of time solution of the heat equation is always the constant function. And so I think if you run this long enough, you'll eventually get the same thing. So probably there's a long tail here. I could be wrong, but I think that's right. Another thing that might make these functions look not constant is that in the end they truncate their eigenbasis, and who knows what happens if you go to a large enough thing. Actually, I guess a large enough neighborhood is okay. It's small time scales that are affected by that eigenbasis.
So e minus lambda IT.
Right. So basically,
away.
Right. So all these lambdas are positive. So eventually you damp away. In fact, there's a proof for you. Sorry. I should have immediately come up with that one. As p goes to infinity, right? All these lambdas are positive. So all these numbers zero out except for one eigenfunction on my surface, and that eigenfunction is the constant function, which has eigenvalue 0. So there you go. Cool. There are other examples here. I don't think it's worth spending a whole lot of time. Just like there's a heat equation, we got the wave equation, and that gives you the wave kernel signature. Now instead of looking as a function of time, like you might expect, the wave kernel signature looks at as a function of frequencies or energies, right? And this yields some multi-scale thing. Right? The HKS has this unfortunate property that it's diffusive, right? So at large time scales, things just start to look blurry. The wave kernel signature doesn't quite suffer from this issue, right? Because at all different frequencies, you're just sort of selecting out different vibration modes. In fact, the wave kernel signature can have the opposite problem, where it's very localized. But anyway, as these folks motivate, we're not going to go into the detail here. You can see that the heat kernel signature can't distinguish between points on a ring around this guy's leg. In theory, it can, by the way, right? We proved that this thing is distinguishing, but in practice, it doesn't so much. The wave kernel signature helps you localize a little bit. And this is only scratching the surface. By the way, yeah, and it has lots of similar problems. But this is only scratching the surface of this huge class of different descriptors that you can write down. Right? But what did I do? I took this object called a Gaussian and I started to play with it. I found its eigenstuff, I used it to solve differential equations, and so on. And each time I did that, I came up with some way to characterize geometry near a point. This is a game that you can play just like ad infinitum here, right? And there's, for each thing you can think of doing with the Laplacian, there's a bijection between those and academic papers that use it for some sort of descriptor. But anyway, rather than spending more time on that, which could take like 3 hours of lecturing in itself. Yeah?
I have one question. Isn't there a concern on the computation of the eigenfunctions? Because
yes.
You have like a big surface with a lot of triangles. You have big matrices, you have to calculate the eigenvalues.
That's an excellent question. You're right. So a lot of these spectral descriptors are written in terms of eigenfunction Laplacian operator, which means that you got to compute eigenfunction Laplacian operator, right? And this is a very unhappy situation, right? So I have two answers for that. One is that for certain descriptors, you can get away with relatively few eigenfunctions. Word relatively here is suspect, right? For the heat kernel signature, I can tell you in practice we usually use between 1 and 200. I know that this is a sort of made up number, but it turns out that it's closer related to the geometry of your surface rather than like your triangulation or something, to some respect. The other sort of the more rigorous argument for why this is okay is that things like for example, the heat kernel signature is diffusive, right? So his job in life is to damp out high eigenvalues, right? So as long as you don't want heat kernel signature values at very small time scales, which starts to just look like Gaussian curvature anyway, you can get away with not computing the spectrum. But you're right, if I have some surface that's composed of like 10 billion triangles, then computing more than like 2 eigenfunctions is not a thing you can do. On the flip side, if I have a surface that's composed of 10 billion triangles, I should hope that those triangles are useful, right? Namely, the sum approximation of a smooth surface, and at that scale, things like curvature and these localized computations should behave a lot better, right? So I can make use of a different class of descriptors. In fact, if that's not the case, then maybe what I really should do is take that bajillion triangle surface and just subsample it, because apparently these triangles aren't adding detail anywhere. But this is all heuristic, right? You're right, this is absolutely a drawback of this kind of technique. But assuming we're okay with computing eigenfunctions of Laplacian, there are lots of things that we can do with it. So for example, maybe I want sort of a stable set of interesting feature points on my surface. The original heat kernel signature paper actually suggests this, right? But what you do is you say now, right, this is one way to think about the heat kernel signature, right? It's the amount of point diffused from x to itself at time t. And I can look at this as, and now I can choose some large t value and look at points that sort of keep the most heat right at their toes. And these tend to be sort of this multiscale idea of extrema, right? And so what comes out are these stable sort of pointy toes and fingers and ears on the surface, right? Now why is that important? Well, if you're familiar with computer vision literature, a lot of times what they do is they'll pick out certain important key points on an image for them. Right. So maybe corners, for example, like SIFT is very good at picking up on corners of objects. Right? It's like hones in right on. And then once you do that, right, you can say, well, look, all 3 of these armadillos here have the same, like what, about 9 or 10 feature points. And now maybe my continuous problem of mapping between these surfaces boils down to first mapping pairwise just between this discrete set of points, and then extrapolating that to the rest of the surface. Right? So it's one toehold into interesting features. A sort of related, broader problem here is a problem of correspondence, which is one that we'll return to a few times in 416. Right? The problem of surface correspondence is pretty easy to state. You know? I give you 2 surfaces, and my goal is that if I point to a point on one surface, you tell me the corresponding location of the other guy. Right? So for example, maybe I have a bunch of armadillos and a bunch of different poses here, and I want to figure out how to make the armadillos talk to one another. Right? Now, one particularly interesting case for today's lecture, we'll return to this when we talk about conformality, is correspondence between isometric or nearly isometric surfaces, which is an assumption that many of these algorithms make. And what's the simplest approach? Well, remember that in reality, most surfaces in the world are rigid. So in some sense, you can think of the most basic isometric matching algorithm as something that actually is just matching rigid surfaces, right? Ones that can't deform whatsoever. There's a very standard technique for this called iterative closest point. And basically those 3 words say everything you need to know about that algorithm. It's really simple. What I do is, so let's say I have a bunch of scans of the Stanford bunny and I want to align them all. What I do is I pick some sample points on x, yeah, we'll call them x sub I. Right, so x will be my source and I want to align it to a target y. I'm going to basically just choose each closest point to each x sub I on the target surface. And then I'm going to rigidly move x so that sort of heuristic set of matches I made, in some least square sense, aligns the 2 surfaces as best as possible. Will we be able to solve this exactly? Probably not. These scans aren't going to align 100%. So what do? Well, now my closest point might have changed, right? Maybe my bunnies started out far away from one another, and now I just brought them together, but they're kind of still poorly aligned. So now I recompute these closest points and I iterate. Turns out this is a really great strategy when bunnies are already pretty much aligned, and it fails very quickly when they're not, but it's a standard thing that you should all have at least heard of. Another strategy we might do would be sort of the simplest possible isometric mapping technique, which is you say, well, what is an isometry? It's a thing that preserves geodesic distances. Right? So maybe what I do is I take my 2 surfaces, like this hand, this way, and this hand with these crunched fingers here, and I literally want to take this guy and unravel him onto the target model. And how am I going to do that? Well, I'm going to just make some small sort of generalized stress tensor, or this way of understanding the type of stretch that's going to happen to the geodesics when I pull one surface over the other. And this technique, which we're not going to discuss a whole lot, is called generalized multidimensional scaling. And basically, it's exactly that. Right? You literally take one surface and deform it onto the other, and you try to accomplish this deformation in an isometric way, okay, without playing with the geodesics. But lucky for us, we already spent the first half or 2/3 of the lecture developing machinery that we can actually just use to help us solve the isometric matching problem. Namely, let's say that I have a descriptor for every point on a surface, right? Remember that the descriptors like the GPS have this nice property that they distinguish all my points on the surface. In fact, they have two nice properties. They distinguish every point on my surface, right? So no two points have the same GPS. But what else do they do? Well, they're invariant under isometry. So what if I have two isometric surfaces? Well, what can I do? I could compute the GPS for every point on those two surfaces. And then how do I compute a map between them? Well, all I got to do is I start at point P on surface 1. I step forward into GPS space on surface 1, and I look at GPS of P. And now I look at my feet, and I notice that there's some point P prime on the other surface, and it's got to have the same GPS coordinate. Right? Why is that? Because GPS is invariant under isometry, and it distinguishes every point. Right? So there's exactly one point on the other guy, which will have the same set of values as me. So then I say, oh, well, he's my match, and then my matching algorithm is done. Way simpler than scaling surfaces and deforming and doing all this stuff. Now, what's the problem here?
Is GPS invertible?
GPS invertible.
Mapping.
Yes, right? We showed that each point gets a unique GPS, which means that you can go from GPS space back. Do you mean, like, could you reconstruct the surface from its GPS coordinates? The answer is yes, but the process for doing that is nonlinear and unhappy. But from a practical standpoint, this sort of closest point strategy is really tough, right? Because chances are, right, these two noisy triangulated surfaces aren't going to have exactly the same GPS at every point. So to do some amount of interpolation in closest point and so on. In fact, there's a slightly different issue, which I haven't mentioned, which is symmetry. Every time a surface has an extrinsic or intrinsic symmetry, you get a repeated eigenvalue in that system we were talking about before. So we're hosed, right? All of our descriptors are no longer unique anymore. In particular, sort of because of isometry invariance, you know that the descriptor on the tip of this hand and the descriptor on the tip of this hand have got to be the same, no matter how hard you try. So are all these descriptor-based techniques kind of hosed? Well, the answer is no for two reasons, right? Maybe what you say is like, okay, well this isn't actually so bad. Now we just have 2 points that go to the same one at GPS space. But now I can, in fact, I can recover two maps, right? The original and the symmetric one. This is sort of a very recent way to think about it. But an easier one is you say, well, I just disambiguate the darn thing, and I give you one pair of points that matches. And in fact, under that condition, right, we started with the heat kernel signature, now we're moving to the heat kernel map. We can now generate a map in a lot of cases. So what is the heat kernel map? Notice, fortunately, I think I've muted my P's, my X's, and my T's a little bit. I apologize. Shouldn't make slides at night. So the heat kernel map is also very simple. Remember that the heat kernel signature is how much heat remains in my toes. Right? Now the heat kernel map is going to say that I'm going to give you a match between 1 point on surface 1 and 1 point on surface 2. Right? In fact, the heat kernel map is just a function of a single surface, so we don't even have to worry about that match. Maybe I just choose a point on surface 1. And now I say the heat kernel map for that point is simply the amount of heat diffused from that one point to all the other points as a function of time. Right, so now I fix the point P, and now I do this as a function of the position on your surface and time, just like before. The time component stays the same, right? This is the time in the heat kernel. But now this is the amount of heat diffused from P to X, right? This is different from the amount of heat from X to X, which is the heat kernel signature. Does that make sense? Well, what does the heat kernel map do? Well, now if I just give you a single correspondence between these two symmetric guys, that's enough to disambiguate left and right sides, right? And now I can generate a map using this nice closest point technique. Right? So what is the algorithm that these guys propose for mapping, which actually works pretty well for surfaces that are at least sort of strongly isometric looking? Well, it's just k nearest neighbors, right? All I do is I give you a single correspondence, which is a pretty weak condition, right? All I'm asking my user to input is literally one pair of points. And now to extract the map, I just compute the C kernel map and then just match a corresponding values. Pretty simple. Right, so the nice thing, so what I want to emphasize in today's lecture is that really we've finally built up all of this machinery, right? Laplacian and cotangents and area weights and all these different things. And while these seem very technical, now all of a sudden we can enable about 25 different papers that all measure different things about geometry, and they're all about 4 lines of code in MATLAB. Kind of cool. By the way, what's one way to think about why this heat kernel map should work and why it's intrinsic? Well, if you recall from a couple weeks ago, one of the ways that we can compute geodesics on a surface is by looking at heat diffusion, right? Namely, if you have a source point, you diffuse heat from that source point just a little bit, and then you can kind of reconstruct the geodesic front from that. What does that mean? Well, it means that your heat diffusion behavior really is encoding geodesic distances from that source point to all the others, right? And maybe one other way of doing isometric mapping would be simply to do that, right? I give you a single pair of points that match. Now I compute geodesic distance to the rest of the surface from those matched points. And it had better be the case, right, that if geodesic distances are preserved, right, in an isometric map, that I can just match the values, right? So this intuition is all linked together. It's kind of nice that we finally have an connection with that. By the way, one thing that I mentioned is a symmetry. Well, what's one way of thinking about symmetry of a surface is as a self-map. Right? In fact, self-maps are very important in differential geometry. We have nowhere near enough time to go through all of the nice math that happens there. But one easy way to find an intrinsic symmetry of a surface is yet again, we compute our favorite isometry invariant descriptors, and now what used to be a bug is now a feature. Right? What used to be our bug in our algorithm was that we had multiple points that were identified with the same GPS, HKS, whatever. But now we step back and we look and we say, well, what points were identified? Well, they were exactly the points that were symmetric. So now I can extract these submaps that tell you what points are intrinsically symmetric to one another. In fact, if you look in GPS space, you can even notice that intrinsic symmetries become extrinsic in GPS space, that actually reflections and rotations and things in there actually makes some sense, and there's some cool math you can do. Now, it warmed my heart the other day because I got 2 completely independent requests to cover one of our own papers that comes in this category, and nothing, talking about the easiest lecture prepare is something that you actually helped write. But a different symmetry that you might find on a surface. So we'll at least motivate it. We don't have time to go through the details. A different symmetry you might find on a surface, also in the class of sort of intrinsic things you can do, is the idea of an intrinsic continuous symmetry. Right? So what are examples that are intrinsically and continuously symmetric? It would be things like spheres and tori. Right? Namely, if you hand me an ideal donut, right? And I hold that donut in my hand, and now you turn around, you put on a blindfold, and I rotate that donut about its axis, and then you look back at the donut. You, assuming that it's an ideal donut, won't be able to tell whether I rotated it or not. Right? In fact, there's this whole class of rotations I can do that don't affect the geometry of the surface whatsoever. Okay? This is an idea of a continuous symmetry. But some of our sort of descriptor-based techniques where we kind of do these nearest neighbors type things, fail in this case, right? Because what's going to happen if I find the GPS of a point on this torus, it's going to have the same GPS as the whole ring here, right? So finding nearest neighbors is kind of a tricky thing to do, right? In fact, you have to be able to distinguish between what's noise and what are actually things that should map to one another. But a completely independent isometry invariant technique is one that we proposed a little while ago that also makes use of the same sort of differential machinery. So our favorite example today is a roll of toilet paper, and not only does a roll of toilet paper contain a developable isometrically deforming surface, but the roll itself has a continuous symmetry. Right? But this is more or less my intuition for what's going on here. Right? That if I have, you can experiment in the hallway when class is over. Right? If you have a piece of toilet paper on a roll here, right? Then no matter how much I roll it around this axis, it still looks like the same roll of toilet paper. Yeah? And as you rotate about that axis, that's going to be the type of behavior that we want to isolate. Right? This is an intrinsic thing, and really what's going on? Well, you could think of the rotation of this roll of toilet paper as a self-map for each time t. Right? So each time t, my toilet paper is rotating about its axis. It gives me some map from where the point started to where it went. Yeah? And what is that map? It's an isometry. Right? So what is the difference between that and like these human isometries that we had before? So this is a function of time. I don't just have one isometric map, I have a whole class of them. But what do you think we're going to do in a differential geometry class? We have a continuous set of deformations here. But we can't help ourselves. We have to differentiate this thing with respect to time. And what does this yield? This yields a velocity field on a roll of toilet paper. Right? Namely, it's where each of these points on the roll of toilet paper is moving from time to time to time. Yeah? And what property does this vector field have? Or this one form? Whatever we like. Well, it has an infinitesimally, if I flow my surface along this vector field, I preserve distances. This is a very different way to think about isometry. Yeah? And it has a name. It's called a killing vector field. Happens to be kind of memorable here. So what are killing vector fields that we know and love? Well, on the plane, there's a very simple one, which is rotation. Similarly, on the sphere, you can have a rotation vector field. And basically, all it is the velocity field corresponding to an isometric deformation. Cool? By the way, why is this called a killing vector field? There's actually a mathematician by the name of Wilhelm Killing here, the middle times of differential geometry. If you'd like to learn about the theory of killing vector fields, be sure to put the word vector, or you will find an unfortunate event in Cambodia rather than mathematical research. But that aside, how can we get to the defining equation for killing vector fields? And then, lucky for you guys, now that we've covered discrete extrusion calculus in some detail, you should be able to follow this paper from that point forward. Let's say that I have, rather than an isometrically deforming surface, I have an asymmetrically deforming curve. Yeah? So how are we going to do this? Well, we sort of have two axes, right? We'll think of S as the parameterization of the curve. Think of T as the set of curves as the deformed one. Right? So in the end, we get gamma sub T of S. So again, S is going to move along the curve, T is going to be which curve you choose. And all these are going to be isometric to one another. Cool? Well, what can I do with that? Well, I've told you that this curve deforms isometrically. In particular, that means is on every interval from A to B along my curve, his length doesn't change. And we have this nice length integral for the length of the curve. Okay, take the velocity. I have taken primes to mean differentiation with respect to S. By the way, does S have to be arc length here? I think I actually know, but it can be if you wanted to. And since this holds for all the intervals from A to B, right? A and B are arbitrary. This thing is an isometry for any little piece of the curve as he deforms. What does that mean? That means that the integrand itself had better be the same for all times t. Yeah, so I can just kind of strip away the integral around the outside. By the way, proof is a word that I use very loosely here. This is a motivation for why this formula should be true. So now what can I do? Well, so we've already sort of dealt with this, let's see here, this S-axis here. But remember that this thing has got to be constant in T as well. Right? That's how we got to this. We have this isometrically deforming class of curves. So what do I do? Well, I say, okay, we know that we showed that at all times t, right, this gamma prime, the norm of this thing, has got to be the same. So if I differentiate that with respect to time, I get 0 on the left-hand side, because this is just at time 0. The right-hand side, I differentiate a little bit, and you can see, so this is the derivative of the norm, right, which is the derivative of the square root of the norm squared. Yeah, which means that I'm going to get 1 over the norm here, and then this thing here, and eventually comes out as this nice inner product. Hopefully right, so what's going to have is gamma prime over its norm is going to give you the unit tangent, and over here, you'll get the derivative with respect to time of gamma prime. Remember, there are two derivatives that I'm kind of hiding in this weird notation here, right? One is along the curve, right, that's gamma prime, that's like the tangent of the curve. And this one is time as the curve deforms. Right, so what did I show? I showed that if I have a curve that deforms isometrically, then he satisfies this nice property that if you take the inner product between his unit tangent and this funky double derivative object here, you get 0. So what does this tell us about life? Hopefully I won't carve with this one layer I got. Well, so we have sort of two vector fields for our curve here. Okay? One is the tangent to the curve, but now if I fix a point on the curve and I look as a function of time, right, that point as he moves around has a velocity, and we'll call it v. Right? So what is this object here? Well, you can think about it, right? So I can take my derivatives with respect to s in either order that I want, right? So you could think, let's see if I get this right. The derivative of gamma with respect to time, if I move that out to the prime, why don't I actually write this down? Okay. Slice out a slide by accident. So we have d over dt gamma sub t prime of s. Right? And this was really hiding two derivatives. Yeah? And since we're in happy calculus land, we can commute our derivatives any way that we want. So let's do that. And that's equal to d over ds d over dt of gamma t s. Yeah? What is this object here? Remember that now I've fixed a point on my curve at position s, and I'm looking at it as a function of time. So this is his velocity as he moves around in space. We'll call this thing v. Yeah? So what is this object? This is the derivative of this velocity vector field of my curve moving around in space along the curve itself. And what does this statement say here? It says if you take that derivative and you inner product that with the tangent of the curve itself, you've got to get 0 out if my curve deforms isometrically. In other words, the velocity of an isometric deformation of a curve has got to be orthogonal to the tangent of the curve. So then how do I extend this to surfaces? Well, if my surface deforms isometrically, well, in particular, if I take any little itty-bitty curve on my surface, then the length of that curve had better stay the same as my surface deforms isometrically. And we know, we talked about it in this class, if you take any tangent vector field, generically you can sort of integrate it for some little bit of time to get a piece of a curve. But it says if I take any tangent vector field t, right, and I compute the same derivative of the velocity field of my surface deforming, expect all this stuff, and I still gotta get 0 for any choice of t. Yeah? This is a defining equation for vector fields that are infinitesimal isometries of a surface. That they fix the lengths of all the curves you can draw on the surface. Cool. Now, of course, this derivative d is sort of extrinsic, right? This velocity could even be like a piece of cloth deforming into space. But remember that we're doing intrinsic deformations, which means they move along the surface. But what did we learn a couple lectures ago? Well, we learned that one way to define this covariant derivative is to take our favorite derivative extrinsically and then project it down onto a surface. Yeah? Well, remember that we're taking the inner product here with t anyway. T is a tangent vector. Right? So we don't care about the normal component of dt of v. Yeah? In particular, this piece of information is perfectly fine. So now we have an intrinsic equation for defining these vector fields. Yeah? And this is one way to compute these isometries. In particular, we might define something called a killing operator. And I realize the terminology here is a little bizarre. But what does this thing do? Well, it takes a vector field v on my surface, and it simply gives me back that inner product at every point in some basis e1 and e2. Okay. By the way, in this class we talked a lot about like 1 tensors and 2 tensors and this and that and the other, and what these things that are this many times covariant, this many times contravariant, and so on. And a fun puzzle to think about at home is what kind of an object is this, right? It's a linear v and quadratic and t, right? So it looks like a little 2x2 matrix at every point on my surface. Yeah, and what are the sorts of things I could do? Well, maybe I ask that subject to V sort of being globally non-trivial, right? So like that his norm integrates to 1 somehow. Maybe I want to minimize the amount of non-killing behavior, right? So remember that generically surfaces don't admit any kind of isometry, right? So which means that even more generically surfaces don't admit continuous isometries, yeah? So in general, this energy is not minimizable to 0, but I may be able to find some approximation of an intrinsic deformation of a surface that preserves a lot of length. So for example, if I take this little bar object here and I minimize energy, what do I get? Well, I get things that sort of look like, you know, deforming a curve with constant length on the 2 pieces that I got. And anyway, to make a long story short, what can we do with these things? Well, for example, if we find eigenfunctions of that operator, it reveals pieces of our surface that are approximately admitting continuous isometries, right? Like, so for example, this little voodoo guy up here, his arms and legs have continuous intrinsic isometries they emit, and they pop right out of the killing operator, which can more or less be computed just using this discrete exterior calculus stuff that we already talked about. Right? Remember that defining equation for killing vector fields? That's something we can totally deal with. And that's the only thing that's going on in this paper that I haven't gone into detail. Similarly, for the eigenfunctions, they actually improve, they pick up little symmetric pieces of the surface. So what are applications, yet another application of either this machinery or some of the Laplacian machinery we talked about. Remember that we talked about segmentation as one thing you might want to do with these sorts of descriptors, right? And there are 2 very simple techniques that have been extended in all sorts of ways for segmentation, right? If we look back at Laplacian and his eigenfunctions, then one thing you might do, for example, for a very simple segmentation technique that I don't recommend, but actually just proposed a couple of years ago, is to just look at the nodal sets of Laplacian, namely the places where it's positive and negative, and use those for segments. And for certain applications, that's actually enough. And they're very stable segments in the sense that you know, your vibration modes are intrinsic and pretty well defined, separated from one another. Similarly, rather than looking for eigenfunctions of Laplacian, which is our favorite intrinsic operator, we now have an example of a second intrinsic operator, which is defined a completely different way. Okay? We can look at eigenfunctions of him, and what does he want to pick up? He wants to pick out pieces that sort of look like cylinders and spheres, and planes. Right? We might use that to get a completely different segmentation. Right? So what do you do when you're designing these sorts of algorithms? Well, you write down the properties that you care about, and then you choose your favorite operator, and usually you compute his eigenstuff, and out comes a nice thing that you can do. And then we'll talk about more in the next couple lectures, is deformation. But remember that in isometry, right, we can flip this on its head, right? So far we've talked about analysis applications where we have a class of surfaces and we want to make an algorithm that is invariant to isometry. But maybe what I do instead is I give you a single surface and I want to deform it in an isometric way. Right? And so lots of machinery that we've already developed can be kind of flipped backward to defining methods for surface deformation. We'll talk about that more next time. And unfortunately, we're low. Well, I've only got 2 more slides. Finally, one more application of all this isometry machinery that I mentioned that I thought I might throw in at the end is that you might, because there have been a couple questions. Again, I warned you guys at the beginning of the lecture today, it's a little bit of a grab bag. Is the idea of computing distance between shapes. So let's say that I download all of Google 3D Warehouse. Pretty big, there's like, what, a couple million random shapes that people have created on there. Right? And my question is, I give you a query shape, like Homer, and I want to find other 3D models that look like him. Right? Well, one way to do this would be to iterate through my database of shapes. Obviously, in practice, I want to pull stuff out. And simply find shapes that are somehow similar to the one that's my query. Right? And doing so, I basically need a distance function, right? One that says that, well, this other shape is this much similar to me, this one is far away, and so on. And in fact, one of the ways that we can formalize this is using the idea of isometry invariance that we've already covered. So for instance, we could define something called the Hausdorff distance between 2 shapes. And what does this do? In fact, it's not even just shapes, it's metric spaces, I guess, but that doesn't matter so much. Well, let's say that I have 2 surfaces, x and y. And this is a very big expression, but it's quite simple. What it says is I play this game. I choose a point x on surface x, and now you give me the closest point on surface y. Just extrinsically for now, right? So I have two bodies sitting on top of each other. I choose a point here, you give me the point over there, and I measure the distance, right? And for each x, I'm going to assume that the point that corresponds to me is the one that's just closest in distance, right? So what's going on here is I choose x, and then I say, I choose the closest y to that x, right? And I look at the distance to the closest point to x on the other surface, right? And of all of those distances between me and my closest point, I choose the biggest, right? So what is this a measure of? It's sort of the measure of the farthest away pair of points. Or rather, the point on one surface that is farthest away from any point on the other surface. Right? And similarly, I can do this symmetrically in y and x and take the mass. This thing is called the Hausdorff distance between these two spaces x and y. So one sort of interesting idea that was introduced would be, okay, so this is a very extrinsic measure of how different two surfaces are. Right? In fact, if I take two surfaces and I just rigidly move them, this Hausdorff distance will pretty obviously change. Okay? But one thing you might do is add one more. We've already had all these soups and imps and maxes and so on chained together. What's one more? So we're going to stick one more in from the outside, which says that the first thing I can do is take my surface and deform him in any isometric way, and then compute the Hausdorff distance. And what I'm going to do is take the inf over all possible isometries of my two surfaces of this distance here. Right? So what does this correspond to? Well, it's sort of, in your head, you can think of it as I have my human model, and the first thing I do is I try and deform him into the pose of the other guy, and then I compute this distance. Right? What this gives you is this nice embedding of shape space with some distance function. So for example here, this is like kind of an unfair test because these shapes are quite different from one another. But in this experiment, these folks took like humans, alligators, cats, spiders, wiggly things, and giraffes. And you can see that when they compute the distance functions, these guys cluster in a very nice way. And so some techniques for understanding databases of shapes are, once again, designed to be at least approximately isometry invariant, and then allow you to do queries and searches and so on. So anyway, so one thing to keep in mind, and then we'll end for today, is that isometry is all about preserving lengths and angles and things on the outer shell of a surface. And that's a very popular notion for geometry processing techniques. But it's important to remember that isometry is not the be-all, end-all solution to your deformation problems. Yeah, in particular, as these folks pointed out in a pretty effective figure in a paper, the glove and your actual hand are two very different objects, right? And if you sit there and take a rubber glove and you deform him in pretty isometric ways, you'll notice that the deformation modes that you might see aren't what you really expect for real-life objects. So sort of an underlying assumption that may not be true for the application you're dealing with is the particular model that's sitting underneath your idea of deformation. So just something to keep in mind. So anyway, today we hit a couple topics from our laundry list of all these different isometry invariant things. This is like by no means the beginning and end of this story, right? In fact, if you look at the Symposium on Geometry Processing, one of the big conferences in this field, you will notice that something like a third of the papers every year try to advertise some amount of isometry invariance for whatever technique they're proposing. So it's important to sort of know the landscape here and understand the basic philosophy of why this is sometimes an important notion and why sometimes it's not exactly what you want. And to understand how to trade off between that is a real skill here. So anyway, we'll stop there for the day. There's no class on Monday. Yeah, it's a holiday. So I guess we'll see you guys on Wednesday. Cool. This guy up. Yeah.